Looking at a hydration reaction that occurs via addition. Hydra in hydration means water. Water, remember, can be split into a hydrogen and hydroxide or hydroxyl group. That water is going to be the second reactant in this organic process. At this point, you know that ation is the action or process of, and so we're going to be adding this hydroxyl group and hydrogen to the double or triple bond of an alkene or an alkyne. Since water is a compound that can be split into a hydrogen and a hydroxyl group, we need to look at the symmetry of the carbons participating in that double bond. If we look at this first carbon, it's got one substituted position with an alkyl group and one hydrogen. The second carbon has one substituted group. It does not matter the size of that substituted group, and one hydrogen. This double bond then shows symmetry, which means that the hydrogen and hydroxyl group could go to either of the carbons participating in that double bond, creating two potential constitutional isomers, where that hydroxyl group is going to go onto that second carbon. So when water interacts, it's going to open up that bond. Now we do need to use a strong acid because that strong acid helps to move protons or hydrogens around. Essentially, the hydroxyl group, that OH, is going to attach to one carbon and the hydrogen to the other. So here we have that 2-pentanol. You do not need to know how to name the alcohols just yet. The groups could have gone to the other side as well, where we would have made 3-pentanol. These two constitutional isomers are going to be formed in relatively equal amounts. Some of you want to know how catalysts work. Again, you're not going to be tested on this. But that strong acid, and you can represent an acid as an H+. Here I've put sulfuric acid there because that is the most common acid we will use in these chemical reactions. But you can see how the strong acid is going to form ions that throughout that process will allow for the transfer of the hydrogens around. Remember, you do not need to know these mechanical processes, but if you like to see what is going on, if that helps you visualize where these hydroxyl groups are going to go, you have this image here. Because we are going to be adding a compound to this organic alkene, we have to look at where the hydrogen and hydroxyl group is going to be placed. Thus, we need to look for the symmetry of the carbons participating in that double bond. To determine if the organic compound has symmetry around that carbon double bond, both carbons participating need to have the same substitution or classification. It will still form potentially two constitutional isomers. However, the quantity of those isomers will be relatively equal. It's when we have an asymmetrical alkene, so that means one carbon has more substituted positions than the other. When that occurs, we need to follow Markovnikov's rule because that will tell us where the more electronegative species is going to bond. So the hydroxyl group that is going to be seeking out electrons is going to go to the more substituted atom, and the hydrogen is going to go to the carbon that already is rich in hydrogen. One way to remember Markovnikov's rule is rich get richer, and we're getting richer in hydrogen. This creates one major product. Here we have an alkene, and because we're adding a compound to this alkene, we have to look at the symmetry of those carbons participating in the double bond. Looking at our first carbon, it's got one substituted position, one hydrogen. The other carbon has no substituted positions and only hydrogens. This means that this double bond is asymmetrical. In the presence of an acid with that double bond, we could, in theory, make two products. However, only one of them is preferential because of the asymmetry of this compound. Using Markovnikov's rule, that acid is going to help open up that double bond. Remember that water gets broken out into a hydrogen and a hydroxide group. What we know from Markovnikov's rule is that the more electronegative group, the hydroxyl, is going to go to the more substituted carbon, carbon number 2 of this propene, allowing the hydrogen to go to the carbon that is already rich in hydrogens, and it just becomes richer. So on paper, we could see that two potential alcohols can form, but only one of them do, due to Markovnikov's rule.